Welcome to the session on polar plot analysis in control systems. In this video, we will understand what polar plots are, why they are important, how to construct them step by step, and how they help in analyzing system stability. Now let's see about the why polar plots are important. So let's begin with the real world perspective. In electrical engineering applications such as power systems, motor control and aerospace systems, analyzing system stability is critical. If stability is not properly assessed means the system may become unstable, equipment may get damaged and safety risk may arise. So engineers need a fast and effective method to evaluate system behavior across frequencies. So polar plot provides exactly what we need. So next one is need for polar plots. You might wonder, why do we need polar plots when we already have Bode plots? So Bode plots require two separate graphs, that is one for magnitude and one for phase. So this makes analysis is time consuming and requires manual interpretation. But if we considering the polar plots, overcome this by combining both magnitude and phase into a single graph, making analysis quicker and more intuitive. Now let's go for the defining stage of this polar plots. That is, a polar plot represents the frequency response of a system by plotting magnitude, that is G of j omega, h of j omega versus phase angle of G of j omega and h of j omega, and in polar coordinates as frequency varies from 0 to infinity. In this plot, the distance from the origin represents the magnitude and the angle from the real axis represents the phase. The positive angles are measured in the anticlockwise direction and the negative angles in the clockwise direction. So this gives a complete visualization of a system behavior in a single diagram. Next we see about the procedure for plotting polar plots. So now let's look into the step-by-step procedure. The step 1 is the determine the open loop transfer function, that is G of S and H of S. Then step 2 is the substitute S is equal to j omega to convert this into frequency domain. And step 3 is find magnitude and phase response of magnitude of G of j omega, H of j omega and angle of J of j omega and H of j omega. And step 4, calculate values for different frequencies from omega is equal to 0 to infinity. And step 5, we have to sketch the polar plot, that is plot values in polar coordinates. Step 6, it is identify the important points such as axis intersections. So let us consider a simple example. G of S H of S is equal to 1 by 1 plus St. So here the magnitude is M is equal to 1 by root of 1 plus omega square t square, and phase we can calculate theta is equal to minus tan inverse of omega t. So by varying omega we can plot the curve and observe system behavior. Next one is frequency domain specifications. So now let's look at key frequency domain parameters. That is resonant frequency omega r, that is frequency at which the system exhibits the peak response. Resonant peak mr, that is maximum value of magnitude. And the third one is the bandwidth omega b, the range of frequencies where system operates effectively. So these parameters help in evaluating performance and responsiveness of the system. Now stability analysis using polar plots. So the polar plots are also useful for stability analysis The first one is a phase crossover frequency omega PC, that is equal to minus 180 degrees. Frequency where phase becomes minus 180 degrees. Next one is a gain crossover frequency omega GC, that is frequency where magnitude becomes 1. And the gain margin GM, it indicates how much gain can increases before instability. By observing the plot, we can quickly determine whether the system is stable or not. Now let's move on to the applications of polar plots. So polar plots are widely used in Nyquist stability analysis, motor control analysis, power system stability studies, aerospace and robotics applications. They provide a complete view of system response across all frequencies. So now let's move on to the summarization part of this video. The polar plots combine magnitude and phase into a single graphical representation, making frequency response analysis a simple and efficient one. Thank you.